Oh, yeah, I think we can start, please.
Okay, sure, no problem. Let me try to keep the full screen of my slides. Okay, let's start. Hello, everyone. My name is Hao-Lan Xu. I'm from Stony Brook University, and I'm a PhD student working with Professor Alexander Zamolodchikov. And today I'm going to discuss the projects we are working together about these analytic properties of two-dimensional Ising field series. And here's the outline of my talk. I will basically start with the very basic aspects of two-dimensional Ising field series, describing what are the parameter space as a parameter to describe the renormalization group flows in the space of quantum field theory and the integral points. And then I will talk a little bit about the properties of the finite size spectrum of Ising field series. Next, I will talk about the numerical methods we are using when doing when researching two-dimensional Ising field theory, using some so-called truncated free fermion space approach to obtain the two-dimensional Ising field theory finite size spectrum. Next, I will discuss the analyticity properties of the inverse correlation length or the fundamental particle, which admits a very nice dispersion relation in the parameter space, and it also shows some very important properties of the Yang-Lee singularities. Finally, if time allowed, I will talk about the ongoing project we are working on about the analyticity properties of S matrix, not only in the parameter space of the scattering, but also in the parameter space of the QFTs. I will talk a little bit about the evolution of the spectrum, about how the meromorphic structure of S matrix change when changing the external parameters, about the particle poles, and some other information of scattering. And the people are welcome to ask questions wherever you have some, where you found I'm speaking about some annoying things or I'm speaking something wrong. People are encouraged to ask questions. Okay, I will start by some very basic point of view about what is the Ising model in generic dimensions. Ising model is defined as you have some classical spins with spins up and spin downs sitting on a lattice with only nearly side interactions. So we can write down Hamiltonian as the nearly side interaction term, and the external magnetic field term is H describes the strength of external magnetic field. And why are we so interested in Ising model? Because Ising model describes the most important universality class in nature. And for example, the vapor liquid phase transition at the critical point and the ferromagnetic transition with scalar point and etc. And it's not only the most simplest, it's the simplest example of the universality class in nature. Currently, we have some nice understanding of Ising models in near 4 dimension, or precisely in 4 minus epsilon dimension. We have the famous Wilsonian picture of the renormalized group flow, as we can do 4 minus epsilon expansion of the 5 to the 4 series. In 3 dimension, right now it's the hotspots of the current research, because people have some numerical understanding of Ising criticality in 3 dimension. We have some numerical solutions like perturbative RG sending epsilon to 1 gives a really nice approximation, and some model Carroll method based on lattice and the numerical conformal bootstrap method. However, in 2 dimension, long time ago, Onsak gave the solution with 0 external magnetic field, with his famous solution of the Onsak singularity of the free edge. However, for generic perturbation J and H, say that in generic temperature and with non-zero external magnetic field, the 2-dimensional Ising model is not fully completely understood and not fully solved. It's not conformal for generic J and H, and it's not integrable. It's still an interesting question to ask: how much can we understand the 2-dimensional Ising model? In the continuous limit, Ising model at critical point would become the so-called Ising conformal field series. That's a special kind of quantum field theory with conformal symmetry. Then a generic Ising model, which not sitting at criticality, would become the so-called Ising field series as the relevant deformations away from Ising CFT. You can perturb From the Wilsonian algebra point of view, it's the perturbing the Ising CFT with the temperature perturbation. Here we denoted the parameter to be tau, and the external magnetic field perturbation, which we denote the parameter to be h. The continuous limit, precisely speaking, means that we shrink the size of the lattice goes to 0, while we keep the normalization of the spin-spin correlate 2-point correlation functions to be normalized. I have to say more about this perturbation away from the CFT. This epsilon operator is the energy operator, which from lattice point of view is the product of a spin with a spin in the nearby side. And this is a local operator well defined in the continuous limit. While the perturbation parameter tau, we define it to be m over 2 pi. Here m would be the mass of the fermion description, which I will mention. I will talk more later, and is proportional to 1 minus T over Tc. So in high temperature, well, it's a convention. In high temperature, we prefer to have tau smaller than 0, and in low temperature, we prefer to have tau greater than 0. That's nothing but a convention. And here, the sigma is the spin operator, which can be regarded as the continuous limit of one single side spin, while this small h is proportional to the external magnetic field capital H. When we define this field theory parameter tau and h, they are proportional to the microscopic descriptions on a lattice. However, the proportional constant is depend on the microscopic description of the lattice. However, it's not important from the field theory point of view. From abstract CFT point of view, Ising CFT can be regarded as a conformal field theory with Z2 unbroken symmetry, which has only 2 local relevant scalar operator. One is Z2 even. We call the Z2 even local scalar operator to be the energy operator, and one Z2 odd local scalar operator, which is the spin operator. Their conformal dimension, delta sigma and delta epsilon, would determine the critical behaviors near the Ising critical point. In 2 dimensions, some diagonal rational CFTs are well classified by what we call.
Can you explain what means Z2 even and Z2 odd?
Okay, sure, no problem. That's including some new language. Okay, so when we see that Ising CFT is a CFT with Z2 symmetry, we say that okay, we can find that Z2 transformation, and this Ising CFT is invariant under it. And when we see Z2 even, that means the wave or any correlation function involving only epsilon, where you do the Z2 transformation, remains the same. However, if you do Z2 transformation to, for example, the wave of sigma operator, you'll find it flip a sign. That's what we describe as Z2 even and Z2 odd. In fact, some more precise description of this Z2 even and Z2 odd, including would need to use the language of what are the topological defect lines of Z2 symmetry. And I know that many people are working on this, working in this group called generalized symmetry in their languages, describing how one can regard generalized symmetries in the language of topological defect lines. But basically, we need that to say that, okay, when we just flip the overall spin of the system, the epsilon is Z2 even one because it remains the same, and sigma is Z2 odd one because if you flip all the spins, then the sigma would definitely flip. I think this answers your question. Yeah. Thank you. Should I continue? Sure. Okay. In 2 dimensions, many rational diagonal CFTs are well classified by the so-called minimum models, labeled by 2 co-prime integral P and Q. Among them, the minimum model 3,4 describes the 2-dimensional Ising CFT. For minimum model P, Q, we can give the central charge and the scaling dimensions of all the operators in this given CFT. Central charge can be roughly understood as the normalization of 2-point function of the stress tensor, and H are nothing but the scaling dimensions of the given operator in the series, with the formulas like this. let's back to the case of two-dimensional Ising. We have the central charge for two-dimensional Ising is 1/2, and we have the nice classification of sigma operator and epsilon operator with their conformal dimensions of, for example, the energy operator, it's 1/2, 1/2. Well, for the left-hand side, we are 0, and right-hand, we are 0. And the scaling dimension of the spin operator is 1/16 and 1/16. By requiring that the action is dimensionless, one can easily read out the mass dimensions of the coupling. Here, this tau or m and small h. The dimension of m is 1, like we usually do, the mass dimension, and the dimension of h is 15/8. From the Wilsonian picture, we can regard the Ising field series as the archery flows away from the Ising CFT. So we can try to define some dimensionless combination of m and h now as the scaling parameters. Here we use the definition of eta, like m over h to some power, and psi with h to some m to some power, which gives the direction of the archery flows away from Ising conformal field series. Now, next, I will talk about some special case of Ising field series. So that's where psi or eta take some special values. You'll find that this Ising field series becomes integrable or solvable, or best simplified. These special cases are, first, when there's no external magnetic fields, it would correspond to the famous Ising solution of weak fermions. And the parameter m, as we have defined before, would becomes the mass of the fermion. On the other hand, if we set m equals 0, however, with non-vanishing external magnetic field, then this Ising field series would become the famous integrable E8 field series. This famous integrable E8 field series, we call it integrable E8 field series because it is not only integrable, but also got a spectrum of only 8 particles, and the mass of these 8 particles corresponding to the length of catons of the E8 group. Okay, another case is a little bit tricky, where we set m smaller than 0, or we are beyond or greater than the critical temperature, and we take h, the external magnetic field, to be a pure imaginary. Then we will find a critical point, another critical point located approximately at this value. It is called the Youngly critical point. And when you getting closer enough to the Youngly critical point, you will find that this Ising field series can be approximately, if you suppress all the irrelevant perturbations, you'll find it becomes the famous Scaling-Youngly model. This is another integrable model with only one species of particle. Now let's back to the Youngly critical point. From statistical magnetic point of view, Youngly critical point are the edges of condensating zeros of Ising particle functions. It also can be understood as, roughly speaking, a kind of Landau-Ginzburg series of phi3 cube series with complex coupling. And in 2 dimensions, from field series point of view, this Youngly critical point is described by the non-unitary minimum model 2,5. This is another minimum model, but however, it's not unitary, with the central charge -22/5. It only got one relevant operator, one relevant scalar operator in the series. We call it phi, with scaling dimension -1/5 and -1/5. Because this only relevant operator got negative scaling dimensions, so it breaks various properties and leads to the series to be non-unitary. And if we deform this Youngly CFT with the only relevant operator phi, we find that it becomes the so-called Scaling-Youngly model. This is an integrable quantum field series with mass gap with one species or only one stable particle, and the mass of particle is related to how strong you are perturbing Youngly CFT with the external magnet with the scalar operator phi. Now, let me show you the big picture and the goal of our project. Our goal is to find out how exactly the properties of Ising field series would change when you change the scaling parameter, when we're changing the scaling parameter psi or eta. And near the critical points or integrable points, we would like to use perturbation theory. For example, if we are near close enough to a critical point, we would use conformal perturbation theory. And if we are closer enough to some integrable points, we would use some form factor perturbation theory built up by the form factor of the integrable field theory. And when away from those special points, perturbation theory would lose its power. However, we would like to cook up some conjecture on analyticity and try to ensure that some parameters would be analytic or at least some nice property in the space of psi or space of eta. Also, we would like to analyze the Ising field theory with some bootstrap-inspired methods, for example, like using the properties of S matrix like unitarity, positivity, cross-symmetry to constrain the form of S matrix or some other observables of the theory. It will be very interesting to see how deep can we really understand Ising field theory, even serve as a serving as a non-perturbative QFTs, even of the simplest one. And here, this picture is a really nice picture about it's a really nice cartoon about the renormalizing group flows from the Ising critical point on the Ising fixed point to Youngly fixed point. And when we go a little bit away from it, it will flow inevitably to the massive Youngly field theory. And when it flows to other end, it will meet some Youngly branch cut, which I will explain in details later. Okay, is there any questions? Okay, sure. Let me continue. Next, I will talk about the numerical methods we are using on this two-dimensional Ising field theory. We will basically use the so-called truncated free fermion space approach. Before introducing what is the truncated free fermion space approach, I will talk a little bit about the fermionic basis, about how one can reduce the two-dimensional Ising field theory to two-dimensional free fermions. Actually, it's not equivalent, but I will explain. At h equals 0, say that there's no external magnetic field. The two-dimensional Ising field theory action is equivalent to the action of two-dimensional massive free fermions. One can rewrite the free fermion actions in this way with our favorite Arrangement operator. Is nothing but the composite operator of psi bar and psi. And the fermionic field psi has mode expansion on the cylinder. One can expand it to be the left moving mode and the right moving mode. However, I have to mention that this is not a CFT because we are talking about massive fermions, so that the left-hand fermions and right-hand fermions are coupled with this mass term. It's different comparing to our favorite case in the two-dimensional massless free fermions in the language of two-dimensional CFT. Never mind, we can still do the mode expansion of fermionic field psi and define the fermionic creation and analytic operator A with the anti-commutating relation. Now, based on the boundary condition on the cylinder for fermionic field psi, the Hilbert space of free fermions will split into the Neville-Schwarz sector and the Raman sector. The Neville-Schwarz sector are anti-periodic on the cylinder, and the Raman sector is periodic on the cylinder. And furthermore, the mode expansion of psi would become depending on whether it's the integral mode or half integral modes. And then the Hilbert space or the Fock space of free fermions would split as a direct sum of Neville-Schwarz sector and Raman sector. However, I have to mention that since we are talking about massive free fermions, it's not possible to split it's only possible to split free fermions Hilbert space into this the the Neville-Schwarz sector for left-hand fermions is equivalent to the right-hand fermions because right now the left-hand fermion and right-hand fermions are coupled together. So so if you determine that we want anti-periodic boundary condition for the left-hand fermion, then the right-hand fermion would also be strictly restricted to be the Neville-Schwarz sector. So this is the only decomposition, or this is the decomposition of Neville-Schwarz sector of the free fermion for Hilbert space, and there's no such kind of direct product between the holomorphic part and anti-holomorphic part in this massive case. Now, however, the free fermion Hilbert space is not equivalent to the Hilbert space of Ising field theory. The Hilbert space of Ising field theory requires that the spin operator, as we have defined, is a local operator and single valued after rotating around on the cylinder, so that we have such selection rules for the number of particles in the NS sectors and R sector. In low temperature, with M greater than 0, the number of Neville-Schwarz sector particle is even, and the number of Raman sector particle is also even. In the high temperature case, the number of particles in Neville-Schwarz sector is even, and the number of particles in Raman sector is odd. And the low temperature case and high temperature case are related by the famous Kramer-Warnier duality, and such selection rules can be easily cooked up by using the microscopic descriptions of fermions on the lattice. Roughly speaking, we can say that the Hilbert space of Ising field theory is equivalent to the Hilbert space of free fermions mod Z2.
Yeah, but sorry, but for mu field, you just have to replace those conditions, right?
Sorry, what
for
field?
disorder, I mean, if you consider disorder field, you just replace like low temperature and high temperature conditions.
Yes, yes, exactly. Because in if you simply replace sigma operator by mu operator, then you are just doing Kramer-Warnier duality and everything's flipped, right? Yeah.
I just thought that in some sense, in Ising theory, you have like both operators. So
yes, you have both operators, but we require that sigma, the spin operator, is local and single value. And since we allow sigma operator to be single value, the mu operator is not single value. If you
probably you're saying that the matrix elements. So the difference is that either the number of Raman particles is even or odd. Probably you're saying that in that case the matrix elements will be 0. Probably this is what.
Yes, it will be 0, or when we cook up the the Hamiltonian, we set those elements to be 0.
Yeah. So, but I mean, in principle, if we would perturb our theory by mu as well, I don't know, for some reason.
Yeah.
In that case, we had to consider like the whole fermionic space. Am I right?
Yeah, the full fermionic space, but we won't call it the.
Yeah. This is
Ising
not what we call Ising theory. Yeah, I see.
That would not be the Ising theory.
Yeah, something else. I see.
Yeah, but that will be, well, but in that case, your Hilbert space will be larger than the Ising Hilbert space. You need not only the untwisted sector, but twisted sector. I think people have very nice discussion about the twisted Hilbert space and untwisted Hilbert space. Some recent papers of those people who are interested in general symmetry. Okay, let me continue about this truncated free fermion space approach. Let's talk about the spectrum. Since the free fermion Hamiltonian is diagonal, well, because the free fermion basis naturally diagonalizes the free fermion Hamiltonian as the ground state energy plus the energy of the self-energy, the energy of each fermion. If we know the cylinder form factor of sigma operator, the spin operator on a cylinder, then we can in principle, we can try to diagonalize the Hamiltonian of Ising field theory on the cylinder to find the full finite size spectrum of Ising field theory. However, we know that the free fermion Hamiltonian is infinite dimensional. So diagonalization of an infinite dimensional Hamiltonian is not possible. However, we can try to cut down this infinite dimensional Hamiltonian to a finite dimensional Hamiltonian and do numerical diagonalization. That is what is called the truncated free fermion space approach. Since we have already separated the free fermion Hilbert space into the NS sector and R sector, the Hamiltonian of Ising field theory now can be divided into blocks. The two diagonal blocks are the self-energy of NS sector and R sector, and the off-diagonal blocks can be calculated by the cylinder form factor of sigma. Say that you have some state in Ramond sector, and it can be, if you apply a single spin operator on a Ramond sector state, it will become a Neville-Schwarz sector state, and the matrix element on the cylinder would become the off-diagonal elements of the Ising field theory Hamiltonian. The diagonal ones are nothing can be computed in free fermion space, although the ground state energy is a little bit annoying, requires some thermodynamic basic answers, and the off-diagonal part requires the form factors on a cylinder. The explicit form of this finite size form factor is a little bit annoying, and if people have more interest, I will show it in the appendix. Now let's talk about the truncation. Truncation means that we cut this infinite dimensional Hamiltonian into finite dimensional, and we would like to only keep states with levels no more than this truncation number capital L. We keep states in NS sector and R sector to be smaller than L. Now the Hamiltonian is finite dimensional, and in principle we can do numerical diagonalization to find an approximation for the exact finite size spectrum of Ising field theory sitting on a finite size cylinder. To reduce the inaccuracy caused by the truncation, we can try to increase the truncation level L as large as possible. And this truncation level L can be, well, approximately think of as something similar to the UV cutoff of this as a UV cutoff. And if you increase the UV cutoff, or if we shrink some kind of microscopic distribution, then this approximate description will be more and more accurate. Here I'm showing you an example of the finite size spectrum of Ising field theory sitting on a cylinder. And many information are readable from the finite size spectrum. This is the finite size spectrum obtained by the truncated free fermion space approach at eta equals 0, or at non-zero external magnetic field, but 0M, say that is sitting at the critical temperature. We say that every energy levels means some asymptotic slope when increase R to infinity, and the slope represents the so-called bulk energy or vacuum energy or free energy of the theory. And the differences between the asymptotic value of the first excited state, second excited state, or higher excited state to the ground state are the energy gaps, and those energy gaps represents the mass of the particle in the theory. For example, at eta equals 0, the first mass is approximately for this number, and the second mass is approximately 1.6 of the fundamental mass. Say M2 is approximately 1.6, actually with further digits, approximately 1.6 of the M1. So you can see that you can try to measure M2 and M1 in this theory, and it's necessary with analytic calculation. And when we're moving away from the E8 point, say, for example, in this case, we are still in the high temperature regime, and at eta equals to some value like this. Okay, forget about this 2 pi to some funny power. This is nothing but a normalization. And at this point, A2 particle is no longer stable, and we find that the energy gap of the second excited state is approximately 2 times the energy gap of the first excited state. That means the second excited state right now can be in the R goes to infinity limit, can be understood as a 2 particle state of the Leibniz particle. And the particle once we call the second particle here, it's no longer a stable particle and disappeared from the stable particle spectrum.
So may I ask,
Furthermore,
sorry, the red curve corresponds to two particle state?
the red curve also corresponding to two particle state, but with non-zero momentum of these two particles. Actually, this green curve also corresponding to the two particle states with minimum momentum
in previous
because they are fermionic. Yeah.
For zero mass in previous picture. So green corresponds to one particle state and red is a two particle state, right?
In this picture,
yes,
the green curve corresponding to the particle number 2.
Number 2, yes, but one particle.
And the red one corresponding to particle number 3 with its mass approximately 1.98 of the fundamental mass. It's close to the thresholds, but not beyond. Yeah.
But do we see two lightest particle states here or no?
This orange line is the fundamental particle M1, A1. And the green curve is the M2, gives M2. Red curves gives M3. And this magenta curve gives 2 M1. However, with the minimum energy, but non-zero because it's fermionic, so you cannot have two zero momentum fermionic particle, right? Because of the Pauli rule, yeah.
But these but these are E8 particles, right?
Yes, these are E8 particles. Yeah.
And all this is for zero moment, something like.
Something like or minimum momentum. Yeah. Okay. Yes, minimum momentum. Yes. Minimum momentum. Well, for two particle states,
Hamiltonian also trivially commutes with the operator of momenta, and you somehow. So this is vector where this second operator acts by zero by some small number, right?
Yeah. Yes. Later on, I will show some more pictures about the mass of this particle. I will focus on the fundamental mass in these slides, but we are doing some research on the higher masses and some other related properties. I will come to that later. So
that means that matrix which you showed, it is in a sense it's block diagonal, right? So you just diagonalize one block of that matrix.
You mean this this Hamiltonian?
Yes.
It's off diagonal, and we do diagonalization to the full Hamiltonian.
Yeah,
so
but
right
now there are infinitely many blocks with given momenta.
Yes.
So.
Yeah. Yes, we do diagonalization to. Actually, we have an infinite dimensional Hamiltonian, and after the truncation, we have a finite size Hamiltonian as an approximation, and we do numerical diagonalization, and the result will be this figure. Okay.
What is L here?
L. Okay, here in this picture, L, the truncation level is 26. Yeah.
26.
36. It takes about 10 minutes to generate all the spectrum here.
Just occasionally coincides with the critical dimension of the string.
Just some coincidence. Yeah, I can see it to be 24, 32, but you can say 30, 34 is critical dimension of the strings -2, right? Okay.
24, yeah.
I'm joking. Okay, let me continue. At pure imaginary age, the spectrum would become complex. However, at pure imaginary age, we still can find a Z2 symmetry of the Ising, of the perturbed Ising field theory, so that this unbroken Z2 with pure imaginary age ensures that the spectrum come as complex conjugate pairs. Here, I'm only plot the real part of the spectrum at this value of, well, okay, I will see at this value of eta complex eta or pure imaginary age. Here we can still observe the first excited state, the gap between the first excited state and the ground state with this non-zero gap, and this non-zero gaps give you the mass. And this is also a particle series with massive particle, and there's only one massive particle in the series. And here I'm only showing the real part of the spectrum. And for some energy levels, it looks as if they merge and then separate again. And in the interval where they merge, they actually becomes complex conjugate pairs, which I will show later. The Youngli critical point is defined or located at the place where the energy gap between the first excited state and the ground state vanishes, and is approximately located at this value. And I will explain how we measure this value, the location of the Youngli critical point. And when we go inside or beyond Youngli, when we go beyond the Youngli critical point or inside the Youngli branch cloud, we can find that even the bulk energy itself, say that a asymptotic slope of every energy levels would also become complex. In this case, you can see that the real part of first excited state and the ground state merge into one single energy level and then go all the way to R goes to infinity. However, their imaginary part would become complex conjugate pairs. So that right now it looks as if your free energy or your bulk free energy is going to develop some kind of discontinuity along this Youngli branch cloud. Even the bulk energy right now becomes complex. And it also works for the higher excited state, so that you find that your first particle mass also become complex. Okay, is there any questions? Okay, I will continue. Next, I will discuss of the so-called inverse correlation length, or the mass of the lattice particle. As was shown, many information are readable from the finite size spectrum. The asymptotic slope of every state represents the vacuum energy of the series, or can be understood as the free energy density of the series, if you from Steinmetz point of view. The asymptotic gap at R goes to infinity gives the mass of particle states. And there are many other information one can read out from this picture. For example, the amplitude or the coefficients of exponential decay of these excited states represents some, well, like the effective coupling of the series, and some merge, some states crossing could give some information about inlet processes. I will talk more about that later. Now let's focus on the inverse inverse of correlation length, or the lattice mass M1. The inverse of lattice mass M1 is correlation length and would determine the exponential decay behavior of two-point correlation functions. And comparing to the higher masses, for example, M2 and M3 and higher masses, the physical meaning of lattice particle M1 is more universal. And especially when M1 goes to 0, you will eventually find some critical point of the series. For generic two-point correlator of some local fields, the form of two-point correlation function with large difference would become like this, with some exponential decay behavior. And we define the correlation length as the inverse 1 over M1, as well as exchanging particle A1. And this A1 is a massive particle, so it leads to the correlation decays exponentially. If we find that the correlation lengths diverge, go to infinity, then we find some critical behavior. Other particles like A2, A3 are considered stable only when their masses were below 2m1, so that it cannot just decay into 2m1. That's the meaning of stable. And let's denote the location of the critical point here. Well, it's actually the Youngli critical point, and at the critical point, the M1 goes to 0. And we know that this is a Youngli critical point, and the critical behavior near the Youngli point is controlled by Youngli CFT. Like everyone knows, its critical behavior is controlled by the given conformal field theory. Let's state very close to the Youngly critical point, and let's say we have below the Youngly critical point, say we are not having complex mass and complex free energy. We can write down the effective action of Ising field theory at this point as effective action perturbing the Youngly CFT with the only relevant perturbation giving the leading critical behavior and all powers of invariant operator perturbations. Those OIs are invariant operators, and also they can be understood as descendants in the Youngly CFT Walmart modular.
Sorry, may I ask a stupid question? This is infrared expansion, right? So this is an expansion. In
Yes, this is infrared expansion. Yes, at UV, it's still easy, right? But we are interested in its behavior at infrared. Where you're not exactly at minus cosine naught, you are flow into the, how to say that? It's the non-critical fixed point where you have, some mass.
I thought you have two parameters. Why everything depends only on xi, but not on
Eta?
No, eta, I remember. Eta is more or less the same as xi. But,
yes, it's cosine, yes.
But you also have the mass. You're not wearing mass here, so somehow why it depends only on one parameter, but not on two parameters? These couplings, lambda.
Yes, that's a good question because actually, okay, how to say that? This. Yes, that's a good. Sorry, is someone speaking?
Yeah, somebody was trying to say something, but
I think it is the limit of large distances where mass is not irrelevant, right?
No, he had two scaling parameters in the UV,
But this Youngly point is corresponds to large distance asymptotics of correlation functions.
Yes, indeed. Okay, actually, yes, actually, I had some very important information here. I did not write down the dependence of lambda or some other parameters on amp here. Actually, the expansion lambda here, this lambda one, it's actually dependent on amp, but I did not write it explicitly because this lambda is dimensionful. It's a dimensionful parameter, not dimensionless. And for writing this effective action, we are more interested in how it depends on the scaling parameter xi. So here I just wrote down the dependence on xi explicitly. The dependence on other parameters, other dimensional parameters are trivial. It can be obtained by simple dimensional analysis. So I did not write it down. Yes, you are right, Alexei. Yep. It depends on M, but I did not write it down explicitly. It's some tricky point, but you can find everything we'll discuss in our paper. Yeah.
Okay, I got it. Thank you.
Yeah. Later on, when I say how we measure this parameter, these coefficients, I would indicate the unit we are using, which actually indicates the unit we are using when we fix M to be 1 or something like that. Okay, let me continue. Here, this OI are irrelevant Towers operators, and they are the descendants in the Walmart modular of Youngly CFT. Since the only relevant perturbation lambda has mesh dimension 12/5, the leading critical behavior is determined by the relevant perturbation lambda. And by simple dimensional analysis, we can know that the leading critical behavior of M1 is given by this finding power 5/12, with the critical amplitude to be, we denote it to be B0. Beyond the leading critical behavior, the sub-leading critical behavior would be determined by all the irrelevant perturbation in the effective action. The sub-leading critical behavior can be, well, the critical exponent of sub-leading critical behavior of some operator OI with mass dimension delta I can be given in this formula by simple dimensional analysis. For example, the leading irrelevant operator, the next operator is the famous TT bar operator with dimension 4, mass dimension 4. So we just plug 4 into here, and we find that it will lead into this cosine square plus cosine naught square to the power 5/6 term in the singular expansion at the Yang-Lee point. And if we focus on this 3-term singular expansion only, and we plug it into the numerical result obtained from the truncated method, we've already found this works quite well with the numerical data.
Sorry, I missed B1 corresponds to what?
Okay, B1 corresponding to the subleading term of lambda.
Ah,
Actually, you can expand lambda into a regular expansion of cosine square plus cosine naught square, and here actually you can write lambda 2 plus cosine square plus cosine naught square to square, and B1 is related to lambda 2. And but if you just focus on, if you try to suppress if you try to delete every term here, then you'll find this expansion is nothing but within this bracket, it's nothing but a regular expansion in cosine square plus cosine naught square. This 5/6 to the power 5/6 can only come if you have some irrelevant terms. Okay. From our numerical results from truncated method, we can read out critical amplitudes with this measurement B0, B1, and C0 in the unit of m equals to 1.
sorry, may I ask, and also I think I was asking something else, but now I realized you studying this expansion along there is only one curve, right? You have like 2-dimensional space of couplings, but there's only
Yes.
one distinguished curve, only one, which connects Ising in the UV and this Liang point. That's why along this curve you have only one parameter instead of 2.
Yes, indeed. Yes, indeed. However, right now, when I'm doing this measurement, I'm having non-zero m. I'm not flow directly into the Yang-Lee critical point. I'm actually, like what I show in this cartoon, I'm considering the curve by cosine square is slightly greater than minus cosine naught square, slightly away from the Yang-Lee critical point. So its infrared behavior dominated by this Yang-Lee fixed point. However, you need to do further perturbation with the Yang-Lee relevant operator away from it. Later on, I will discuss this flow directly hit the Yang-Lee fixed point at infrared. I will talk about it in a while.
So psi greater than minus cosine naught squared corresponds to massive phase. Right?
Yes, massive phase. Yes. You can only measure some non-zero mass in some massive phase, right? Otherwise, you'll find that this this m goes to 0 when you exactly hit the Yang-Lee point. Of course, I cannot measure some number 0 very accurately, so I do not have a point here. Yeah.
So the correction B1 correspond to T var, it's correct?
No, C0 corresponding to TT bar. B1 corresponding to the subleading contribution to the regular expansion of num.
Okay.
Yeah, thank you. Okay, here in this unit, when we fix the capital M into x1, we can read out the numerical result of the leading and the subleading critical amplitude. And this subleading critical amplitude, typically this C0, gives us some information about the effective action of the expansion. Before talking about furthermore about the effective, the couplings in the effective expansion, first we want to find out the location of Yang-Lee critical point numerically. We define some R to be M1 over this cosine square plus cosine naught square to this power, and from its behavior approaches a constant, we can try to read out the location of Yang-Lee critical point in very high accuracy. These two plots show the show how it approaches the constant, and one can read out B0 from this constant. And this number matches quite well with some other methods, maybe not based on the field theory, but based on some lattice computation. Now, let's talk more about the critical amplitudes and subleading critical amplitudes. The expansion coefficients determines the couplings of the excited actions. For example, if you looking at the Yang-Lee field theory, the mass of the fundamental particle is related to coupling lambda with this formula, with this constancy Yang-Lee given explicitly in analytic form in literature. It's obtained by thermodynamic basic answer. Unfortunately, I do not have time to describe it, but I can tell you that it's exact and given in explicit closed form. Thus, we can read out the relevant coupling number 1 out of the leading critical amplitude B naught to be this number. And the subleading one can also be read out from the mass coupling relation like this. For higher singular terms, the proportional coefficients of the irrelevant perturbation is related to the 2-point form factor of the corresponding operator. For example, if we have some irrelevant operator O, then its perturbation to the singular expansion of M be in this form, with this given singular term and the 2-point form factor. However, fortunately, in this case, our leading irrelevant contribution is generated by the famous TT bar operator. And everyone knows that this TT bar operator is in some sense solvable. As a result, the coefficient C naught is related to its perturbation explicitity. Let's denote the perturbation coefficients to be alpha over pi square in this TT bar term. Then we have this alpha naught can be calculated in this number with this constant F Yang-Lee. Well, I will tell you what is this F Yang-Lee is next page. How it comes first. So let's consider the TT bar deformation of a series. A TT bar deformation is deforming the series with the TT bar operator built up from the stress tensor, or roughly from the contracting the stress tensor T mu nu, and another T mu nu with epsilon tensor in 2 dimensions. Based on the famous factorization property of TT bar operator, one can show that the finite size spectrum of the TT bar operator satisfies this Burgers equation explicitly, which quite works well for every energy level separately. The solution of this Burgers equation shows that the deformed spectrum is nothing but the original spectrum with a shift in R. As a result, after the TT bar deformation, the free energy and the fundamental mass got the explicit form of deformation with undeformed mass minus this alpha and F. In our case, we can try to approximate the undeformed series as a Yang-Lee QFT, so that this perturbing with TT bar operator leads to the explicit term with this alpha times F times M1, and we will find out that this F Yang-Lee is a constant in Yang-Lee field series. Yeah, with this F equals to F Yang-Lee M1 square. This F Yang-Lee is minus square root of 3 over 12. It's a constant representing the free energy, how free energy density related to the particle mass in Yang-Lee QFT. It's obtained by thermodynamic basic answers. And one can simply express F naught in terms of C naught. Okay, is there any questions? Okay, let me continue. Next, I will talk about the spectrum flows exactly into the Yang-Lee critical point. When we take psi square exactly equal to minus psi naught square, that means the spectrum at large R would be dominated by Yang-Lee CFT, not QFT. And now we can suppress the relevant deformation term. We can delete the relevant deformation term of the effective action. So the effective action is nothing but the Yang-Lee CFT perturbed by the irrelevant operators, where I wrote not only the leading irrelevant operator, but the next leading one. The next leading irrelevant operator is what we call psi. This operator is the level 4 and level 4 descendant of phi, which in our understanding breaks integrability. I will talk more about how it breaks integrabilities later. We can roughly label the energy eigenstates in Young-Lee CFT with the classification of states in Young-Lee CFT at infrared with the left dimension and right dimension, H and H bar. Then the form of energy eigenvalue at large R is dominated by the Young-Lee CFT. So the form is explicitly by this 1 over R term and the free energy term, the bulk free energy term, which is the CH H bar. It's the Young-Lee central charge minus 12H minus 12H bar. This CH and H bar is now as effective central charge. To help further analysis, we define some function C as a function of R for every energy level, which is defined in this form, and which should approach the effective central charge at large R. The deviation from constant at large R can be expressed using conformal perturbation theory, as we can try to calculate the matrix elements of the irrelevant operators in Young-Lee CFT. It can perturb giving the corrections to CR at large R. By calculating the matrix element, it's quite easy to calculate such a matrix element, but it's a little bit lengthy, just doing contour integral as everyone knows from the big yellow book, but I'm not showing the details here. Now let's talk about the states. The lowest 5 states are the 2 primary states. The ground state is not a corresponding to identity, but phi, because phi got minus 1 over 5 minus 1 over 5 for the scaling dimensions. So the ground state is phi, and the first excited state is identity. And the second identity are the starting from the second excited state, they are the descendants of the of the primary states, and with their effective central charge to be these numbers. And from the plots here, we find that each curves approaches this constant, this effective central charge nicely well when R goes to infinity. Now, inspired by the previous TT bar deformation formula, I can try to undress the TT bar contribution by shifting R into R with this given alpha naught and the energy level. And we do this fine shift of energy level for each energy eigenstate separately. And it looks as if you are obtaining some spectrum obtained by some effect reaction without the TT bar term once you choose the correct perturbation coupling alpha naught. In practice, we can try to plot En or Cn against this new defined shifted R, and it's looked at it's given by the action absent of the TT bar perturbation. For example, if we consider the first excited state, it's labeled in the Young-Lee CFT as corresponding to the identity operator. One immediately realized that this the metric element of the level 4 and level 4 descendant of phi is and this. Now, in this case, the leading irrelevant operator psi is 0. So the spectrum, if we choose the shifted spectrum by comparing the shifted spectrum or the shifted C should approach this constant quickly if we choose a correct TT bar coupling alpha naught. And this is how we double check our measurement of alpha naught comparing to the previous result of singular expansion, and it's matched quite well.
So
To measure, yes.
what?
You have some question?
Yeah, can you comment on this cartoon? What you're basically computing here? Is it? It's not related to the fermionic truncation approach. It's another approach. It's
actually right now I'm using the spectrum obtained by the truncated method. I already got the spectrum at hand, and right now I want to read out more information from the spectrum. And we know that at this point, the infrared behavior is controlled by the Young-Lee CFT. So At the infrared behavior, it's controlled by the Young-Lee safety, and perturbing the Young-Lee safety, the leading irrelevant operator is TT bar.
Mhm.
And we try to strip off the TT bar contribution to see what is happening at the next level. First, for the first excited states, we know that TT bar irrelevant perturbation dominates.
Numerics, probably this is obvious, but that does numeric confirms the exact solution of TT bar perturbation. So if you do not turn on next descendant, you will numerically find perfect agreement with what TT bar predicts. I mean, the energy levels, everything.
Yeah. Yes. And I'm choosing the first excited state because for the first excited state, the next irrelevant perturbation is absent.
I don't understand. On this cartoon, where is the infrared region? So
The infrared region we can understood as R goes to infinity is the infrared region. And every curve here approaches constant because it's dominated by the Young-Lee safety. Here I'm plotting C. The C is it's the constant. It should approach the effective central charge.
why you have so many? So
Well, here I'm comparing different, doing TT bar undressing or doing this affine shift with different parameter, and we want to find out whether our measurement of alpha naught was correct.
no, I don't understand why the vacuum in CFT is degenerate. Or so you have three states of the same energy in the
Those are the same state. Those are all the first excited state.
These are just for different alphas. I see.
Yeah, this is the affine shift after different alpha naught. Sorry, I should have explained it clearly, but by choosing this blue curve, which approaches the constant nicely, we can read out the correct value of alpha naught.
And the red curve is what?
Red curve is the one without TT bar undressing, the original curve. This red curve
Without.
it's this curve itself. Well, it's minus C. Yeah, it approaches. This is minus C, and this is plus C. So it approaches this constant from now.
But it approaches different value in the infrared, or it just missed it?
It approaches the same value, but I just unable to plot it to very large R. Because this truncated method cannot extend to very large R, otherwise the truncation effect would come into the game, and it loses numerical accuracy.
Yeah, and it looks like there's some singularity approximately at two plus something. So what is it? It is that
it should be some higher irrelevant operator. The behavior here is control some higher irrelevant operator, and I guess it would be the T to the cube, T bar to the cube, I think. And we have no
Hagedorn transition point. No, it's different. No, it's not.
It's different. It's not Hagedorn. It's not Hagedorn. It's nothing but the higher irrelevant perturbation in this effect direction. Yeah.
Okay.
Well, to be strictly speaking, this TT bar undressing is only a method helps the numerical analysis, and if you go to very small R, then it does not make any sense. I have to say that, because you know that after TT bar deformation, you are having some serious in UV, you are facing trouble.
And also, am I right that the smaller R you want to probe, the more levels in the truncation you have to take, right? Is that right? So
Sorry?
I mean, the lower values of R you're trying to probe, the more values in the more levels in the truncated approach you have to consider. So I mean,
if you want to approximate the spectrum at a large R more accurately, you need to increase the truncation level.
Yeah.
Larger R.
Yeah, but here is other way around, because this is infrared perturbation in a sense. So for larger R, it's not important that you include high levels, but for smaller R, right?
Yeah, for smaller R, yes, you need to, okay, you need to add more term for the irrelevant
Yeah,
action.
for error.
For the effective action, yes.
Yes.
But this is different than our truncated method. This truncated method is something.
I mean, not even taking more terms here, but also taking more levels in CFT, which you also truncate.
Yes, yes, more levels in CFT. More levels in CFT. Yes, you're right. More levels in CFT in the effective, or higher terms, higher irrelevant terms in Roman modular of Yang-Lee CFT. Yes, you are right. Okay, are there any more questions? If not, I'm continue. Now we are interested in the next irrelevant operator, this psi, with then we can try to measure the numerical value of the perturbation here, beta naught, by looking at the second excited states with using conformal perturbation theory. With conformal perturbation theory, we can compute the matrix element of this operator, level 4 descendant of phi, and to be this number, and we can try to do fitting of the undressed this function C for the second excited states. And the fitting works like this, and it reproduces the really nice result about this numerical value of beta naught in the effective action. Also, we know that this operator psi is very important because it breaks down the integrability. We also know that this energy level merge and becomes conjugated pair behavior can never happen in an integral field theory. So that we know that this this kind of level crossing, well, level crossing actually becomes conjugate pair, is a signal of the breakdown of integrability. So we can try to look into how good this operator psi reproduce this kind of behavior. Now let's focus on the third and fourth excited states, their crossing behavior. That. And this blue curve and red curves are the C2 and C4 from data. After do the TT bar undressing, they are the curve here in the magenta line and the brownish line. And these two states lies quite close to each other, so we can try to regard them as a two-state system. We can compute the matrix element psi 33, psi 34, and psi 44, and regard this two-state system. After solving a quadratic equation of this two-state system, it predicts quite well of this signal of this behavior of them merge into each other and becomes conjugated pairs. So that we can say that this beta naught psi term perturbation is the mainly cause of the breakdown of integrability.
Why the crossing break the integrability?
Sorry?
Why the crossing break the integrability?
Oh, that's a good question. Yeah. Integrability means that you have an infinite number of commuting okay, so let me see this. Integrability means that you have an infinite number of commuting conserved charges. So that if you have two energy levels, if you have two energy levels cross at each other, that actually means you have two states with the same energy. You have roughly speaking, you have two particle states at the same energy. And if it, okay, let me show you some picture. If you have two energy levels cross each other at one point, that means you have at this time, at this radius, you have some two different particle states roughly with the same energy. And integrability ensures that there's no inelastic scattering processes. So there's nothing but a cross. However, this is at eta equals 0, where this integrability is present. However, where you not have integrability, these two particle states of these two energy level represents would interact with each other and lead to some cross, lead to some off-diagonal matrix elements. And this off-diagonal matrix element will lead to some, in this case, some kind of recursive behavior of two energy levels like this. Or, well, this recursive behaviors happens at the unitary series, and in the non-unitary series, it's possible to have this merge. Or otherwise, that means you have some off-diagonal matrix element between one particle state and another particle state. And that's nothing but that's a result of inelastic scattering, and inelastic means you do not have integrability. I hope this answers your question. Thank you. Are there further questions? Okay. Let me keep going. Now let's take a step back and review what is the Yang-Lee branch cut. We have this Yang-Lee critical point, and the Yang-Lee branch cut can be understood as zeros on Yang-Lee circles condensed in the continuous limit as a branch cut. And this branch cut is a branch cut for free energy and also for M1. In high temperature within the Yang-Lee branch cut, both F and M1 becomes as complementary conjugate pairs. And the discontinuity is a pure imaginary value due to this unbroken Z2. Once someone formulate the imaginary part of M within the Yang-Lee branch cut, it is possible to establish the analyticity relation on the complex chi-square plane to give any value of M in this plane, and this is what is called the dispersion relation. Now let's first list the conjecture. For M1 at high temperature, the conjecture is that the Yang-Lee branch cut is the only branch cut in the complex chi-square plane. So, and other than the Yang-Lee branch cut, M1 is analytic, and there's no other funny behavior in the U-plane or complex chi-square plane. Then we can write down the dispersion relation as follows, representing M1 in any place of this complex chi plane as an integral along the Yang-Lee branch cut of the discontinuity. And due to the unbroken Z2, this discontinuity is related to is exactly 2 times the imaginary part of M1. Of course, we can try to measure the imaginary part of M1. However, such measurement from the finite size spectrum is of low accuracy. And a better way is try to extend the expansion of M1 along the both ends of the branch cut and try to establish the discontinuity as the extension of expansions at both ends. Beyond the Yang-Lee critical point, we have the singular expansion dominated by the singular behavior, the critical behavior at the Yang-Lee critical point, and we can easily do analytic continuation from below the Yang-Lee critical point to beyond the Yang-Lee critical point. On the other end, that is the place where you find eta equals 0, and that's the famous E8 field theory. Near E8 field theory, M1 has a regular expansion in eta, follows perturbing E8 field theory with the energy operator psi. And it's a regular expansion in eta and for real H. And we can easily do analytic continuation from real H to complex H, and from eta to complex eta, and obtaining a regular expansion of M1 in complex eta at the another end of the Yang-Lee branch cut. Here we define eta equals to minus y to this final power of 4 pi over 15, but when h takes pure imaginary value, y is real and negative. In y coordinate, the Yang-Lee branch cut is located between minus y naught, here this point, and 0. And the full high temperature domain is squeezed into this sector, what people call high temperature wedge. And the singular expansion at the Yang-Lee critical point here can be extended and be analytically continued within the branch cut and the regular expansion at eta equals 0 and eta real can be extended to here in the branch cut. And by matching two expansion, we cover the full Yang-Lee branch cut. We can obtain a nice numerical approximation of the discontinuity of M1 along the Yang-Lee branch cut. And this is what we did. This is the, well, actually I'm plotting -y. Here I'm showing the discontinuity of M1 along the Yang-Lee branch cut. And it matches quite well with some measurement of immeasured part of M1 within the Yang-Lee branch cut. We have numerically, we have extended the single expansion with 3 terms and try to match the regular expansion at eta equals 0 and as a nice approximation, numerical approximation for the discontinuity, and it works well. Since we have the discontinuity of M1 along the Yang-Lee branch cut, we can try to check our dispersion relation, this mass dispersion relation, and compare it with the data we have measured. And here I have shown everything in this plot. Those bullets, no matter whether they are purple, red, or green, or blue, were the measurement from truncated method from the finite size spectrum data. And the dashed line were the results from the dispersion relation. And everything works well so that we can show that our conjecture about the analyticity property of M1 in high temperature is correct. Okay, is there any question? Okay. If not, let me switch to another topics. And let me continue and switch to another topics about the analyticity properties and the evolution of scattering processes in Ising field theory. From interacting quantum field theory point of view, scattering matrices are the most important measurable quantities of the theory. And all information of this interacting QFT should be encoded in the S matrices and the scattering process. Not only S matrices, but also the inelastic processes. But I'm not going to talk more about it. In 2 dimension, because we are in 2 dimension, the kinetic information of scattering becomes simplified. For example, in 4 dimension, the 2 particle coming in, 2 particle come out scattering has 4 Mendel stems and has 3 Mendel stems, and the 3 Mendel stems are not all independent to each other, and we have 2 independent parameters of the Mendel stem. However, in 2 dimension, we got only 1 independent variable. Let's consider A1 particle and A1 particle scattering, and we define the scattering matrices to be in this way, where you have an in-state of A1 particle with rapidity θ1 and θ2, and the S matrices can be understood as the measurement of the outstate A1 with θ1 and A1 with θ2 in a product with A1 and A1 with in-state. And here, those dots represents the inelastic processes, which I'm not going to discuss more later. Where we have denote the θi as the rapidity of the particle coming in particle. And this S of theta is our favorite S matrix. Now, let me list some property of the S matrix. First, because theta is the rapidity, so it means the periodicity property. Theta is equivalent to theta plus 2 pi I. Crossing symmetry replace theta to pi I minus theta, or you can understand as it changes the T channel scattering to S channel scattering and vice versa. Unitarity requires that S of theta times S of minus theta is equals to 1, and the reality requires that S of theta equals to S star with minus theta star, among which the unitarity hold for real theta and for those scattering without particle equation, say that it's the energy of incoming particles are not high enough to create more particle. Yes, please.
What?
Sorry?
Star means what?
Oh, star means complex conjugation. Complex conjugation, yeah. Just taking star for complex numbers. That's it. complex conjugation. Yes.
Okay.
Yeah. And okay, unitarity hold for real theta and theta below the inelastic processes. And sometimes you can even find some unitarity properties for non-unitary series scattering. And the reality is required by asking the stable particles in the series with the real mass. Now, with the above conjecture or the axiom for the property of S of theta, you can write down the generic form of S of theta, which we have defined the imaginary part of theta between plus pi and minus pi to be our principal shape, so that the generic form of S of theta can be separated as the meromorphic part with various poles and zero within the principal sheet and some phase. And this phase is the inelastic scattering phase, and those poles and zeros has corresponding physical meanings. Let's define the physical strip to be imaginary part of theta between pi and 0. And in physical strip, there are only real particles. Otherwise, the causality, macroscopic causality would be violated. And those real poles in physical strip corresponding to the stable particles. And below the physical strip is the mirror strip, where the imaginary part of theta between minus pi and 0. And within the mirror strip, you can have complex poles, and those complex poles and the real poles represent the resonance states and the virtual particles. The status of theta is the inelastic phase with the corresponding optical theory, so that the inelastic phase is related to the total inelastic cross-section of the series. Now here is a cartoon of the some of the asymmetrics at eta approximately to be this value. And here I use circle with cross to represent the poles, and the empty circles to be with zeros. And here we have alpha 1 pole, real alpha 1 pole here, and pi minus alpha 1 pole here. And this is the S channel pole for some scattering, and this is the corresponding T channel pole. And this is some scattering for another, this is another scattering. Sorry, this is another pole for this scattering, and this is its cross pole. And we can also allow some complex pole in the mirror strip here. Now let's talk about some special cases. At integrable points, there are no particle creation, so the inelastic scattering phase is trivial, it's 0. And S of theta is a meromorphic function. And the stable particles represents is equivalent to some real poles in physical strip. And the location of the real poles in physical strip is related to the mass of the stable particle with this formula. For example, alpha pole here, alpha 2 pole here represents two A1 particle coming in, exchange particle A2 in S channel, and then become two A1 particle again. And you can compute the location of alpha 2 with the mass of mass M2. For example, if we consider the self-coupling, for example, two A1 coming in, exchange the A1 particle and coming out, then we find that alpha 1 is 2 pi over 3. And this alpha 1 is 2 pi over 3 is the self-coupling of A1. It's located here. And at T channel, at this cross channel, is alpha 1 bar at pi over 3. It's here. First, at free fermionic point, we have the trivial scattering, with S of theta is nothing but -1. When you're infinitely getting close to the Youngly point, we have only one particle, and this one single particle, and this one single particle would have self-coupling. So the F of theta is in this form, with only pole at alpha 1 pi over 3. At the E8 point, a more interesting case happened at the E8 point. At the E8 point, there are 3 stable particles below the stable particle threshold. Those are M2 and M3 with the mass here and here. Sorry, here should be cosine and cosine. And we can write down the explicit form of S of theta in this form. For genetic cosine or genetic eta, the analytic structure of S of theta would become more complicated. First, first there are more poles in the mirror strip, and second, there are the inelastic processes would appear so that we have inelastic cross section. We have the branch cut of F of theta here and here. Because you have non-zero inelastic scattering sections, the inelastic branch cut will extend from the inelastic threshold plus or minus theta inelastic to plus or minus infinity. Meanwhile, poles are allowed to sit within the mirror strip, and the poles in the mirror strip can be understood as virtual states or resonant states. On the other hand, only part of the information, the S matrix here, can be readable from the finite size spectrum directly. We can only know the masses of the stable particles easily from the finite size spectrum by looking at the energy gaps of the eigenstates. However, virtual states and resonant states cannot be easily read from the finite size spectrum of the Ising field theory on a cylinder. So we actually do not really know where are the poles here in the mirror strip. However, the evolution of F of theta along continuously changing psi or eta should be also continuous, say that poles or zeros of S of theta should not appear or disappear from nowhere. That actually gives us a very nice picture of how this S of theta should evolve when we change psi or eta continuously. For example, gradually decrease cosine square from plus infinity to 0. We are changing our picture from the E8 point to the free fermion point. And we know that at free fermion point, we got only one particle, which is fermion. And at E8 point, we got three stable particles. Well, at least three stable particles at E8 point. So the number of stable particles decreases when we're moving psi square from plus infinity to 0. The number of stable particles decrease, and on the analytical structure of S of theta, it looks as if the real poles in physical strip would move into the mirror strip. And also at cosine square equals 0, this self-coupling A1 pole also disappears from S of theta. So we can see that, okay, some 0 would cancel with the pole at alpha at 2 pi over 3. And we know that this 0 actually coming from the particle number 2. Okay, this is the cartoon of, this is a picture of how the analytic structure of S of theta would change when we decreasing cosine square from plus infinity to 0 and then to minus cosine square. Or we can try to understood as changing eta from 0 to minus infinity, then from minus infinity to the Young point. Alpha 1 and pi minus alpha 1 represents the lattice particle self-coupling. So the location of alpha 1 and pi minus alpha 1 should always be there. However, alpha 2, alpha 3 would disappear. So A2 and A3 should disappear from the stable particle spectrum, so that this alpha 2 pole should actually move from the physical strip to the mirror strip when we changing cosine square or changing eta. And also there's some unknown puzzle about alpha 3, because when we finally reach minus cosine square, we got only alpha 1 and alpha 1 bar, and there's no alpha 3 and alpha 2. Where are the alpha 2, and are they moved to infinity, or are they observed by the index branch cut? That's something what we do not really know. Okay, we are trying to describe the evolution of the S matrix quantitatively. However, we are mostly in the non-perturbative regime, so perturbation theory, no matter whether you are using the conformal perturbation theory or form factor perturbation theory, cannot help much. However, for some quantity of F of theta, it's possible to establish the corresponding dispersion relation, like what I discussed about this inverse correlation length M1. And this corresponding dispersion relation can tell us some information about the full evolution of the two-dimensional Ising scalar matrix quantitatively. For example, we can define this B factor to be the residue of S of theta at the self-coupling point 2 pi I over 3. And this residue is proportional to the square of effective 3-point coupling of A1. And this can also readable from the finite size spectrum at coefficients of the leading exponential decay of the first excited state. And it is possible to establish the dispersion relation for B and check such kind of dispersion relation against the numerical data. Another example is the inverse of sine alpha 2. It represents the location of the pole alpha 2, and it also admits corresponding dispersion relation when we change psi square or change eta in the high temperature domain. And it can tell us when and where alpha alpha 2 reach some point, and when and where it goes to infinity or not. To establish such kind of dispersion relation for these parameters of the S matrix, the key is to find the corresponding discontinuity along the Yang-Lee branch cut. And to establish such kind of discontinuity, it's possible to use perturbation theory to similarly use the expansion at both ends of the branch cut. And for example, near the Yang-Lee point and the E8 point, we can both use the form factor perturbation theory by computing a form factor, a 4-point form factor for Yang-Lee QFT or for E8 field theory. It's possible to extract some part with the kinetic information and with some reduction of the kinetic information, and this what we call F regular, the regular part of 4-point form factor would determine the deformation of S of theta, the scattering matrices, when using the form factor, the local operator O as a perturbation away from the integrable field theory. And this is an ongoing project, so I do not have further plots to show, but it looks as if we have established such kind of dispersion relation, and it works quite well, and it can tell us more information about the H matrices. And we expect these papers about for some more dispersion relation will be coming out soon. And finally, let me give a summary of my talk. This is the end of my talk, and let me give a summary. I have reviewed what is the 2D Ising field theory is, talk about some very basic aspects and the numerical approaches to two-dimensional Ising field theory. The mass of the lattice particle M1 has a singular behavior at a Yang-Lee critical point, and we have measured the critical behavior at a Yang-Lee critical point and determined the effective expansion of the Ising field theory action near the Yang-Lee critical point. We also look deeper into the property of the Yang-Lee critical point, about the location of Yang-Lee critical point and the breakdown of integrability. We also show that the M1, the lattice, the mass of the lattice particle M1 has some very nice analyticity property, and which is called the mass dispersion relation. We have shown that it's correct. And finally, I have discussed some evolution of S of theta and some other dispersion relations. And the goal is to understand the series space of two-dimensional Ising theory non-perturbatively with both analytical and numerical methods. We have run into many difficulties when doing these projects because some of part was coming from the limitations of numerical method, and from some other aspects coming from our not fully understanding of the analytical method. For example, the form factor perturbation theory is extremely complicated for E8 field theory, and it becomes more involved if you try to do some perturbation theory away from the E8 integrable field theory. And there are some ongoing unsolved questions about some evolution of cis theta in low temperature case. In low temperature case, the Ising spectrum can be described as a Manson spectrum, and there are some classical or semi-classical approaches to describe the spectrum and we are looking into the evolution of S of theta in low temperature. We are also very interested in the high energy scattering behaviors and the asymptotic behavior of theta, and we believe it's related to the inlet scatterings in a very fancy way. And that is basically my talk today. Thank you very much. Hello, is there any questions? Is everyone still there?
Yes, sir. Thank you.
Thank you.
I guess Alexei left somewhere, so he's not
Yeah.
answering.
Is there anyone have some questions?
Thank you very much.
Yeah, thank you. Thank you for listening.
Yes, sorry, I had to go to open the door. So questions, or you, everybody asked questions already. Does somebody have a question?
Or maybe some comments.
Come
I'm
on.
more welcome to comments rather than questions.
So what you were talking about, the scattering matrix relates mostly to the high temperature phase, right?
Yes, but yes, you're asking a good question. Yeah, we are also looking at the low temperature phase. Yes, we have some very interesting results, but I'm not going to show it today.
Okay.
In the low temperature phase, it's the that when you're getting close, when you're having small age, that's the Manson spectrum, right? By the famous McCoy-Wu scenario. And since it's a Manson, then the spectrum of Manson can be approximated by semi-classical quantization, and the scattering can have some classical treasury of the Manson scattering, and there are many nice properties of it. I think Sasha is working on it, and I'm also working on it. Yeah.
But if the temperature, if you are in the complex plane, it's not easy to distinguish between high temperature and low temperature phase. If you allow the parameters temperature and magnetic field to take complex values, right?
Oh yes, you are saying about allowing complex temperature, right?
Yes, but you were talking about Young-Lee singularity. This means you are considering complex coupling parameter in the Ising field theory, right?
Yes, but here we have already assumed that our temperature is real.
Okay.
But I'm also very interested in what would happen if we extended the temperature to be complex. But for now, it's a little bit difficult to imagine to have a complex temperature.
Okay.
I know some people. I know that Professor Robert Schrock in Stony Brook got some results in complex temperature about the lattice Ising model. In complex temperature, he finds some very interesting pattern, but unfortunately, I'm not fully understood of the picture. How this Young-Lee circle would change in complex temperature. I'm not fully understood of what would happen. Yeah, but for now, I prefer to consider high temperature and low temperature, not complex temperature for now. But yes, that's very interesting, and I'm willing to look into that in the future. Yeah, thank you.
Other questions?
Are there other questions?
Okay, if no, let's thank Hao-Lan.
And thanks everyone for attending my talks today.
Thank you.